Hi physics students. So today we are going to work on the answer key for worksheet 2, and this is a worksheet that is representative of the spring lab that we did in class today. So the first question gives you this equation, and it asks you to fill out the chart and to graph it out. So you're determining the amount of force given that the stretch, the delta x, is 0, 0.05, 0.1, etc. meters. So this is pretty easy to do. You're going to take these values. Since it's your delta x, you are going to plug it in to that delta x part of your equation. And I'm going to have you do this on your own, but the answers you get for this are going to be 0, obviously, 50, 100, 150, 200, and 250. Pretty simple math. The next, and this is all in newtons, the next step is to graph it. So anytime you graph, you always want to look at what your maximum values are for your x and your y axis. For the x-axis, I go up to 0.25. So if I count this out correctly, I start with 0, and I increase by 0.5 each time. Sorry, 0.05 each time. And I should get my last line to be 0.25. Same thing with my y-axis. I'm going to plug in my forces, and I'm going to go up by 50 newtons. And of course, you want to make sure to label, this is the force in newtons, and this is the stretch in meters. So now you want to plot your points. I'm going to use a little bit bigger of and then you're going to make a nice straight line out of that also. So as best as you can, you would use a ruler, draw a straight line through that, and that gives you your graphical representation of the force of a spring and the distance it's stretched. The next step is to graphically determine the amount of energy stored while stretching the spring, and this one is focused on a 0 stretch to 0.1 meters. So anytime you are looking at a force distance graph or a force stretch graph, you can find the energy stored through the area under the curve. So this is area under force stretch delta x graph. So I am going to highlight just that area between 0 and 0.1, and it's a triangle, and you all know how to find the area of a triangle. So the area is equal to 1/2 base times height, which in this case is 1/2 0.1 times 100, and that gives you 5 Newton meters. So energy can be represented in two types of units: Newton meters, which would be the units for the stretch and for the force, but you can also represent it as joules, J for joules. Okay, the next one, we are going to find the area under the curve, but this time we're going to find the area between 0.15 to 0.25 meters. And this one is a little bit tricky because it's a trapezoid. If you know the area or the equation for the area of a trapezoid, go ahead and use that. But the way I do it is to break it up into a triangle, because that's easy for me to memorize, and a rectangle. So I'm going to do this in two parts. So the area of a triangle is going to give me 1/2. My base is from 0.15 to 0.25, which is 0.1. And the height is from 150 to 250, which is 100. I already did that calculation here, so that gives me 5 joules. And then the area of the rectangle, is equal to base times height, which in this case is a base of 0.15 to 0.25, again, 0.1 meters, and then a height of 150 newtons. And so in this case, our answer would be 15 joules. And then, of course, we're going to have to add these two together. 5 plus 15 equals 20 joules. All right, so we're going to go on to question number 4. It gives us a diagram and it gives us some information as well. So it tells us a spring has a spring constant of 10 Newton meters. Anytime I'm given information, I'm just going to go ahead and write out my givens. Spring constant is represented by K, and that value is 10 Newton meters. It tells us that the block is being pulled a distance of 0.3. That's my delta X, 0.3 meters. And then it tells us to find the force. So my unknown would be to solve for the force. Now, my equation for solving this would be force equals K delta X. And I can plug in those values. But before I do that, it also tells me to sketch a force body diagram. So I'm going to do my force body diagram here. Before I do that, I want to circle my object in question, which is my block. And then you want to think about the long range forces that are acting on it. So for this block, I've got obviously the force of Earth, or the force of gravity. I've also got the normal force of the surface. And those are equal and opposite because the block is not moving. And then I've got the force of the spring. The spring is opposing the pull of the block. So that would be the force of the spring. And then, of course, there's the force of the person pulling it to the right. So the force applied on the block, or the force of the person on the block. It says the block is not moving, so we would call these balanced forces, and I'm going to go ahead and label them as double symmetry lines here. Okay, so now what we want to do is we want to solve for the force on the block. We know the force of the spring and the force applied are equal, and I'm just going to use my equation. So I'm going to substitute my values, and I'm going to plug in my K and my delta X, and when I solve this, I end up with a force of 3 newtons. Now it's asking us for the force of the spring. The force of the spring is pulling in the negative direction, so you want to label that it is left. Or you can put in negative in front of your answer. All right, so we are going on to problem number 5, and this one is analyzing a spring force stretch graph. And it's asking us to determine the spring constant. The spring constant would be the slope of a force delta X graph, specifically spring force and stretch. So I'm going to do it for the triangle data and for the rectangle data. And all I need to do is find the rise over run. So I'm going to choose, if I look at this data, 1 is right there between 0 and 2. And I like this point because it gives me nice values. So I'm going to choose 0, 0, and 1, 8. So this is 1, 8. and I'm going to plug it into my y2 minus y1 over x2 minus x1. So I'm going to start with 8 minus 0 over 1 minus 0. That gives me 8 over 1, and I get a spring constant of 8 newtons per meter. The second one, let me just erase this here. I'm going to use a different color. So the second one, I've got this point right here, which looks to be about 1,5. And right there, I'm going to again use 1,500. So I get 5 minus 0, y2 minus y1 over 1 minus 0, x2 minus x1. You could also do rise over run, which is, I think, easier. I get 5 over 1, which is 5 newtons per meter. So that's my spring constant for the triangle and for the rectangle. The next step is asking for the force required for a stretch of 3 meters. So what we're going to do for the first one, this is for the triangle, I'm going to go to 3 meters, which is right here, and I'm going to find out what that force is just by figuring out what its value for force on the y-axis would be at 3 meters. So in this case, the force is equal to 24 newtons. Another way to do it is just to use your K value that you got from 5 and multiply it by your value 3. Both of those would get you 24. The rectangle's force, if I go to 3 all the way up, I get somewhere around just below 16, so I'd say that's 15. And so I am going to write down 15, but I want to verify that. So I'm going to use my equation. Force is equal to K delta X, and I'm going to plug in my K, which is 5 Newton meters, and I'm going to multiply it by the distance that I want to determine for the force, which is 3 meters, and when I multiply that together, I get my 15 newtons, which is exactly what I estimated it to be. Okay, so this next problem, we are solving for the elastic potential energy, and we learned that the elastic potential energy is the area under the curve. So I'm going to start with the triangle, and I'm going to highlight this area under the curve here. It's a triangle, and so that is going to give me 1/2 base of 3 and a height of 24. And when I calculate that value, I end up getting 36 joules, or you could call it 36 Newton meters, which are the same thing. And then for the triangle, or sorry, for the square, I am going to do the same. It is also a triangle, a little bit smaller. So for that one, it is 1/2 base of 3 again, and a height of, we calculated this to be 15 newtons. And so the answer for that one would end up being 22.5. 22.5 Newton meters, or you could call it 22.5 joules. All right, so this very last problem is asking us to determine the amount that the spring needs to be stretched in order to store 24 joules of energy. So this is a problem I would always start with my givens. The energy is equal to 24 joules. And then the unknown is the delta X, how much it's going to be stretched. Now, we're focused on spring number 2, which is my my triangle. Data set 2, which is this one right here. And we're only given one piece of information, it seems, but we also know something about the spring, which is the spring constant. And we solved for that in question number 5. The spring constant is 8 Newton meters. So this is a really good problem to start with the givens because we've got 2 equations that we could use, or 2 equations that are available to us for energy. And that would be your equation energy is equal to 1/2 force times delta x, or energy is equal to 1/2 spring constant times delta x squared. Well, we have a spring constant. We don't know the force when it is storing 24 joules. We only know the force when it is stretched 3 meters from question number 6a. The 24 joules is not the same distance as 3 meters. So we can't use this force as part of this equation. So I'm going to cross off the top because I know that the spring constant, no matter how far it's stretched or no matter how many joules it's holding in energy, is always going to be 8. It's a constant no matter what. So I am going to use this bottom equation to solve. I'm going to substitute my 8 Newton meters. I'm going to solve for my delta x squared, and of course I forgot I need to erase my energy because I have that value also, which is 24 joules. So when I solve this, 1/2 of 8 is, 1/2 of 8 is 4. So I'm going to take 24 joules equals 4 Newton meters times delta x squared. And then when I divide the 4 to the other side, I end up getting 6 is equal to delta x squared. But in order to find delta x, I have to take the square root of that. And your answer will end up being 2.44 meters. And that would be your final answer.